Today's conversation is with Alexandre Belin. Alex is a theoretical physicist at CERN, where he primarily works in quantum field theory. His research involves the exciting frontiers of physics, such as string theory and quantum gravity. We enjoyed exploring Alex's work and discussing how beautiful grand questions like the unification of relativity and quantum mechanics can be answered through the combined efforts of scientists. This was balanced by going into depth about some of the unpleasant aspects of science, such as the publish and perish mindset in academia. Overall, we learned that from Alex's advice and experiences that science is all about fun. And here is our conversation with Alex Belin.
We'd like to start off just by having you tell us about your career. What do you enjoy the most about being a scientist? What have been some of the highlights in your career?
Great. So maybe I should start very quickly telling you about myself. So
Yeah.
I was born in Geneva, Switzerland, actually where I am now. I looped, even though I went all over the world before. So I did my undergrad here. Then I went to McGill, to Canada for my PhD. Then I did postdocs at Stanford in California, then in Amsterdam, before coming to CERN. So yeah, that's like an overview of my career. Yeah, what do I enjoy the most? I think doing science is extremely exciting. Can be frustrating at times as well. And there's many highlights. It's hard to pick out just a few moments. I think it's a bit like a sine wave. So there's sometimes where nothing's working, and then everything starts to click, and you understand stuff. And so and there's a lot of those moments. They sort of come frequently. There's also a lot of the frustrating ones, but that's what makes it very exciting. So of course I could pick out, maybe like a prestigious conference where I gave a talk or a paper that I wrote that got a lot of good feedback. Those would be sort of like, CV highlights. But in terms of life experience highlights, I think I think there's maybe many more of them, and they come along every now and then, which is really a lot of fun. Yeah, and then maybe just mentioning one other thing is that I organized a conference in the Caribbean one year, like 3 years ago, and that was really great. I mean, to have a bunch of physicists on the beach chatting physics, going for a swim, playing volleyball, and going back to do physics in the evening. It was really, really fun, and everybody that was there enjoyed it. And we're doing it again this year, like 3 years later. So that's maybe another highlight.
Yeah. So you mentioned that you traveled a lot, when you were studying. So just do you think that's like a necessity for like younger students who are going through the ranks of undergrad, then masters, and so forth, PhD, or do you think you can get by without having to travel?
It depends a bit on the fields of science, but overall, yes, mobility is something that is important. It's both important for you and your development, because if you say your whole career in one university, you'll learn one way of thinking. But every time you move for a next step, you'll see how things are done somewhere else, and that'll be, an enriching experience, and you'll get to be like, oh, okay, you'll learn a little bit of a new way of thought. So every time you join a new group, you learn new stuff, and that's what helps you develop as a physicist. And also, of course, it extends your network, because then you'll know, the whole group from all the places that you go. So that's at the level of your personal development. And then, we're constantly evaluated in science, because we have to apply for jobs or we have to apply for grants. And then one of the things that they'll evaluate you on is mobility. There's like, for example, I just applied for 2 grants that I handed in the last weeks. And then there's explicitly a place where they sort of evaluate your mobility. That's just one of the criterias. So moving around is very important. And also, not just temporarily. I think this is something that I forget. I was rereading this morning your question, the like 5 questions, and you're saying, what are the key steps, and what do you wish you had been told maybe more clearly at the beginning? it's very important, I think, if you're really committed to a career in science, to realize that it will require moving along the way, and then it might also require you, settling in a completely different country than where you started, or maybe even where you wanted to go, because there's few jobs, and you will not be able to decide if in your field the job opens in Australia or Switzerland or Japan or I don't know, Sweden or India. Sometimes it is what it is, and so mobility is really also vital at that stage. Maybe I should just say, that being said, there are other fields, and I know of nobody basically in physics that has stayed in one institution their entire life and did a career this way. But there's other fields, tied to, like, maybe say environmental science, where you end up working a lot with say, I don't know, if you're in risk management or crisis management or whatever, and then you end up working a lot with the authorities of your country. So those are sort of, fields that have like stronger impact and link with government and society. And sometimes those fields, it's easier to stay in the same place. Sometimes it can even be encouraged. But I would say, that's like, those are rare within all the fields of science. If you're in biology, chemistry, physics, math, like mobility in some form is an important factor.
Right. So, sort of speaking of these institutions, tell us a bit about CERN, because personally, my idea of what CERN is very much attached to documentaries like Particle Fever, and that sort of glorified image of CERN, which I'm sure it's great, but tell us about the whole picture. What about theorists and other scientists?
Yeah, CERN is amazing. It's also so different from all the other places that I've been. It's not a university. It's a research institute and more, and it's basically a small town. So it's at the very edge of Geneva, and it overlaps between both France and Geneva. It also has several sites. I'm at the main site, but there's also several sites for CERN. And it's very different in the sense that, all the other places I've been, you're on some form of campus or another. And, there's undergrads walking around, grad students, professors, but it's like, it's a university vibe. I don't know how else to describe it. CERN is different. CERN feels more like a little town where there's a ton of activity. There's close to 10,000 people, I think, every day, at least before COVID, 10,000 people on site every day. That's really huge. And those are not just scientists. There's also contractors of all sorts. CERN has its own police and its own fire department. So it's really like a small town. That's sort of the zoom out view of CERN. That doesn't impact me too much every day, because the theory department is right next to the sort of main entrance and the visitor entrance, let's say. So we're very close to like the HR offices, and we have, our 2 floors of offices. That itself looks very much like any other physics department you would find, or a theoretical physics department you would find in universities, say, once you're inside the building. And, and then we go to the cafeteria. Instead of having a bunch of students that are also having lunch, you have all the other people that work at CERN. But from the inside, it looks very similar. One big difference between CERN and universities is CERN is a research institute, so it doesn't really have graduated students. So you can't do a PhD at CERN. Of course, some of the they're not really called professors, they're called staff members at CERN. It's the equivalent of a professor. They may have PhD students that are attached to a university somewhere. So there's like, a handful of PhD students that are there. But usually in most physics group, the biggest pool of people in the group are the PhD students. And that doesn't happen at CERN. So it's a bit different. It's more, people that are there tend to be more senior in their career as well. But yeah, overall, it's very exciting, and you definitely get the feel that like you're at, one of the epicenters of physics, for sure.
And this is a more specific question. It comes in light of the fact that we've just finished applying to university, where we're selecting all of our units and so forth. And I have a question about maths, right? What mathematical concepts do you think are very important for us to study in our undergrad years for that applies to all of the sciences, not just physics? What do you think are the core concepts that people should learn?
Interesting. I could tell you very clearly what applies to physics, but now you're asking a more general question.
I suppose physics works as well, if you have
Yeah,
that.
so for physics, it's really, and I think that's the sort of math classes that I had in my physics curriculum, and it's really analysis and algebra. Those are really like the two, linear algebra is very important for many different fields, but in particular quantum mechanics. And then analysis is important, I mean, just throughout, derivatives, integrals, and so on. And I think that's probably in general in science, you'll need analysis and to some extent algebra for almost anything you do. And then another thing that comes to mind that was less, I mean, now I'm working on some form of statistical physics, so it's directly relevant, but maybe it was a bit less relevant earlier in my career. But in many experimental fields, statistics is just extremely important because that's how you tell if your experiment worked or not. So that's another, I think, third maybe direction of the math axis that is important.
Sure.
It's also very fun. I mean, well,
Yeah.
I find it very fun.
Yeah.
I know experimentalists sometimes are like, this is the part where I have to go do the statistics and find it frustrating. Right. But I think it's a fun field.
Sure.
Right. You sort of mentioned this before, but talking about large-scale international collaborations like CERN, how are they generally organized and completed? How do scientists really get involved in the projects? And even a step before that, how can students get involved in those collaborations if possible?
Right. Okay. So there's various scales of international collaborations, and by picking CERN, you've picked, I think, essentially the largest structure that or one of the largest structures that exist. I mean, CERN is really, really gigantic, and something like CERN is so gigantic that it has to happen at the political level. There really has to be a political will. Scientists, were not the ones to decide that CERN. Scientists were, of course, very involved with the creation, but the decision to do something like CERN, that has to come from the political side because it's so huge. And so, countries got together. This happened after the Second World War. I could send you guys. There's some notes written on the creation of CERN that I think are very enjoyable to read. And so if you're interested in this, it's like, I don't know, I forget, like 50 pages, and it goes through, how CERN got created, and what were the developments in terms of physics, what was the role of CERN throughout the first few decades. I think there's a part 2 that talks about 1990 to present or something like that. But those are pretty fun. So if you're interested, I could send you the link, and probably you can put it on your blog or whatever. That's pretty fun. But CERN is the biggest possible structure. Then there's other international collaborations that are still what I would call huge but smaller, where say 15 to 20 professors, or as they call it, principal investigators, PIs, get together and say, okay, listen, this is a very interesting topic that's happening right now. Let's write a collective grant application all together. And we're gonna, try to put a particular effort in this direction. And then they apply to various grant agencies. It could be the European Research Council in Europe, or it could be the NSF in the NSF in the US. Or private grants sometimes, and they get together and then they get the grants, and then each PI will hire some students, some postdocs, and it forms like a big collaboration. And so now we're talking, I don't know, the scale is maybe 50 to 100 people. CERN is in the tens of thousands. I think the number of affiliates. So I said 10,000 people on site, but if you count all the people that are external but still linked to CERN, that's more like 20,000 people. So that's like, the biggest possible scale. And then, but these international collaborations, they can be, say, order 100 people, and that's already very big. And then there's various other scales that exist that are smaller, and there's probably some in between, although, there's other big labs like CERN that are maybe in between, not as big as CERN, but the same style, and that came from the same type of concept. And now you're asking, how how do we get involved in these collaborations? These intermediate scale collaborations, say order 100 people, you have to sort of already be in science in one way or another. I mean, you can apply for a PhD in that field, or you can apply for a postdoc, but that's sort of the only channel. CERN has a zillion possibilities because it's so big. And in particular, they have a huge internship program. And I think, well, I know many people that I think they do it. I think there's a program while you're in undergrad to come. There's like this visitor program where you come and do a small project. I would have to do the research, or maybe you guys looked into it already, but there's definitely many internship possibilities that you can do while at CERN, like summer projects or whatever. And actually, I know many people in my field that did that. While they were in undergrad, they were excited about CERN, and they came and they did a small summer research project. And some, return 10 to 15 years later as a postdoc, and they're like, oh, I haven't been here since I was doing my project in undergrad. So that's definitely something that you should look into. And I don't want to say that CERN is the only place like this, but CERN is definitely very unique for this, in the sense that it really has a lot of these internship programs, and many people end up doing it. So I highly encourage you or anybody else that would be interested to look into that.
Right. That's great to hear that there are undergraduate opportunities as well. And my next question is more about lab work. As a theoretician, I assume lab work isn't, maybe it's not it's a big part of your career, but what is it really like, even as a theoretician or experimentalist, to be involved in lab work? And in that terms, what are the pros and cons of being in labs in, again, large institutions like CERN?
Yeah, that's going to be hard for someone like me to give an answer to, because not only am I a theorist and not an experimentalist, but also I'm a theorist working in a field which is sort of the furthest you can get from experiments. So there's some people at CERN that are working on precision calculations directly relevant for the Large Hadron Collider, for the LHC. I'm on the more formal part of the theory department, where I'm working on string theory and black holes, and subjects where currently there's not so many experiments that you can do to test directly what we're working on. We hope that that'll come in the decades, in the following decades, but I'm sort of very far away from experiments, or at least what experiments are today. So it's hard to do. I mean, my last contact with an experiment is my second year of undergrad, where I had some optics lab or something like that. So it's a very long time ago, and it's far away from what I do. And I have to say, I don't really understand exactly how it works for an experimental physicist. Say somebody working on the LHC, the experiment is so gigantic, everybody must be working somehow in their small corner, and it's like putting all of this together that produces the amazing results. But this process, I have to say, I'm a bit blind to it. So I think it would be more useful to ask directly an experimental physicist working at the LHC, for example, what their day-to-day life is. I know there's a huge amount of data analysis. So of course there's the engineers that build the experiment, but I think now somebody that's an experimental physicist working on the LHC, I don't think he's like necessarily on site, staring at the big at the tubes or whatever. I think it's just like they receive like raw data, and then they need to process it, and a big part of the job is processing the data.
Right. And you sort of opened a segue to this question, and I was hoping to leave it to the end, but I know it's not going to be an easy job, but if you would like to, could you explain to us a bit of your research that you've done recently that you like to talk about, and in terms that maybe, I'm sure it's going to be difficult, but understandable for us as well.
Sure. So I work on. So what my research focuses on is quantum gravity. So there's two pillars of physics that you'll learn in your undergrad, if you do a physics undergrad, which is quantum mechanics. It's how we describe physics at the very, very small scales. For example, particles and their forces and how they interact. There's a framework called quantum field theory to describe that, and we understand that very well. And then on the other hand, there's gravity, how stars move, how the galaxy evolves. Now we can even observe black hole mergers through gravitational waves. And that's all very rich, but that's classical physics. So it's not quantum, it's all classical and works on very large scales and works for gravity. And one of the big challenges, if not the biggest challenge that we face in fundamental physics is understanding how do we put together gravity and quantum mechanics to have now a quantum theory of gravitational interactions. The sort of microscopic particles of gravity, the gravitons, how they scatter in a quantum mechanical way. And you might think, well, you just do that. You put them together and you run with it, but that doesn't work. And you run into inconsistencies. There's famous paradoxes that arise when you try to do that, in particular involving black holes. And so that's the big aim that I'm trying to do, and the route that I'm going is to try to use string theory, which is a framework that can put the two together, and in a consistent way. And okay, that's sort of like the big picture. And then my particular work is that I'm really right now trying to understand statistical properties of black holes. So one thing that we learned in the 70s through the work of Bekenstein and Hawking is that, so black holes, we think about them as a black hole where nothing exits, and that's true classically, but actually quantum mechanically, there's a little bit of radiation coming from black holes because there's pairs of particles that can be created very close to the black hole horizon, and one falls in and the other exits, and then you can detect it far away. So black holes actually do radiate a little bit. They have a temperature. It's a very small temperature, but they have a temperature. And they also have entropy. And entropy is a notion that you'll learn about in your thermodynamics class or statistical physics class. But it sort of counts, it's supposed to count the number of individual microscopic degrees of freedom of a system. If you think about gas in a room, well, we just say, okay, there's air in the room, right? But air is made out of atoms. There's millions of them, and they all have their own particular configuration that they can be in. And we don't study each microscopic configuration, but we say the air has entropy, which is a very large number, which counts all this number of configurations. And one thing that we've learned is that black holes carry entropy. So that should tell us what the microscopic degrees of freedom of a black hole are. But we don't know what they are, and we realize that there's a huge amount of them through the work of Bekenstein and Hawking. I'm trying to understand how to think about this problem from a statistical point of view. What can we say about the statistics of these microscopic degrees of freedom?
Right. I have a question.
I hope that was vaguely understandable.
Yeah. So you have a question that's huge, right? Trying to merge like gravity with quantum physics, right? That's like massive question. That's I suppose you could say it's sort of a paradigm, right? It could be sort of paradigm shift that gets answered. But how do you think academia as a whole approaches questions as big as that? Like, what's the practical process of trying to answer huge questions like that? How does it work? And then I suppose how do you get leading on from that, how do you get involved in that, I suppose?
Yeah, that's another great question. So first of all, the big questions that are unsolved, it also means that there's been typically decades of research on them, right? So it's not like today we're like, oh, I just realized quantum gravity is an important question. What do I do? It doesn't sort of work that way. It's like people formulated quantum field theory and general relativity a century ago, and then things move on. And so the initial conditions today are not just a big question, but also all the work that has done to arrive where we are. And for example, finding a theory of quantum gravity, that's a big question. Saying, how do we resolve, say, Hawking's information paradox? Hawking's information paradox says that, take a very, very, very complicated amount of stars and galaxies and whatever, and you all collapse them into a black hole. And then, as I said, the black hole radiates, so very slowly it'll evaporate. But by the time it's done evaporating, the evaporation is simple, if you want. It's just like a thermal object. So, there's only one number that characterizes it. It's the temperature. And so by the time it's done evaporating, all this complicated information about the galaxies and all the structure, it's lost. And you're left with just temperature, basically. And that violates quantum mechanics, the unitarity of quantum mechanics. So now all of a sudden, let's confront this paradox, for example. And that's a much more concrete question, right? It's still, if you want, a giant, but it's a much smaller giant. And that's sort of how we work. We take the big question and then we're like, okay, what's an avatar of how hard this question is? It's this paradox. Let's try to address this paradox. And then we build a mathematical framework or a toy. Physics really, I think, works by toy models. We're trying to find what's the simplest possible toy model that shares the maximal number of features with the real question that we want to solve. That's, so, sometimes we go down in dimensions, or we remove some of the degrees of freedom, but try to keep just enough to make the problem interesting. And we sort of try to work that way. And so, we have a big question, then we have a particular paradox that we want to address. Then we find a toy model in which there's a same form of this paradox, and we try to study the toy model, and we sort of move like that. But sometimes you spend a lot of time down the rabbit hole, and it's only at the end of a very long adventure that you can say, okay, I think I understand how it works for this toy model. How far up can I go back to really, tackle the question that I started with? But I'd say that's sort of how it works.
Sure. And so the next question, we want to move more away from academia and just learn more about yourself. So the question is, why did you choose to become a scientist? Why that over some other career? Like what? So yeah, how did you come to that decision? And I suppose deep in that, like, what do you think motivates you to continue being a scientist?
Right. So yeah, that's a great question, of course. So both my parents are scientists. They're both biologists. I'm sure that played a role in one form or another. It was very clear that I was not going to do biology, but also I think very clear that I like science. So of course that played a role in this. And by the way, this is, I think, why what you guys are doing is absolutely great, is that, I could just ask my parents, how did you go through this? What choices did you do? Most people that want to do science don't have that, right? So they have all these questions and it's not clear who to ask. So that's why I think it's great that you guys are doing this, so that if people want to know more about it but don't really know who to ask, they can just watch your blog. So that's why I'm highly supportive of what you guys are doing. But so I think that was some of my initial conditions, and then the rest, I think at some point you're in high school, you realize that, you really enjoy math and you're good at it. I think that's sort of where it starts, because you get math before any other science class. And then you go to high school, you start having physics classes, you enjoy those as well, and you're good at that as well, and that's sort of how it rolls. And it wasn't clear at all that I would do physics. I mean, halfway through high school, I was more into chemistry, actually. But then I started having like advanced classes in physics, and they were really fun. And sometimes all it takes is a good or bad high school teacher in physics, and it sends you the physics way, or it sends you away from it's a bit of random fluctuations. And I had a really great high school physics teacher, and then that was it. And then within physics, I think what I realized quickly is I wanted to understand. I was driven towards the more fundamental in some sense. So for me, it was not so much an issue of not working on something that has a direct life application, but I wanted to understand, how does the world work at the most, and you sort of follow the arrow of the most fundamental, and then you kind of land on quantum gravity. So that's how it worked for me. And then, there's various choices along the way, like experiment vs theory. I think overall this is being recorded, so I should be careful. I'll say it anyway. It's okay. Throughout my undergrad, I mean, there's many classes that I enjoyed, but my impression, the classes that I enjoyed the most and where I thought, the professors were the most razor sharp with their answers happened to be the theorists. I always thought that my theorist professors were somehow, I don't know, maybe they just had a way to put things in a way that I would understand, but also every time I would ask a question, I would get a razor sharp answer. And there was this trend. So I tend also to be more amazed by my theoretical professors. And so I think that played a role as well.
Sure.
And sort of speaking of that, this is as a person who wants to pursue physics, this is a question that I have, not even starting to learn the big concepts, is that finishing the undergraduate course, sort of going through what is almost known in physics, and then to the postgraduate, and after that, where most of the big research is done. How does one actually choose their sort of minimal, like very specific topic, like you did in terms of quantum gravity? Because there seem to be so many different pathways, and making choices hard.
Yeah, I think a big uh, sort of the person that has the most influence in this regard is your PhD supervisor, because say you're gonna do your curricular in physics. I mean, there's choices. There's obviously choices. For example, in many places, general relativity is not a mandatory class. You can take it if you want. So if you're interested in gravity, you're going to take that one. So there's choices throughout your physics undergrad. And then sometimes you have to, I don't know if in Australia there's a master's program. There isn't in the US, so it depends where, but often there's a master's program, which is in some places, mostly classes, but you do a research project. And of course, who you do it with will also influence a little bit. But usually, by the time you're done with your master's, you've also listened to some talks and you've followed enough classes that you kind of get a general idea of what you're interested in. And I knew I wanted to do quantum gravity, but it was not 100% clear that I would do string theory, or like I didn't know that much. I mean, I had to learn a bit of string theory during my master's, but this was kind of my general thing. And then I started looking for people doing research, in the direction that I liked. And then I applied to a bunch of places for PhDs, and then you land somewhere, right? And then your PhD supervisor is going to give you projects, at least at the beginning, and that'll sort of influence like which sort of direction you go in. And then you specialize that during your PhD, and then life as a postdoc is about taking one or two steps back and enlarging your horizon and learning about other things, and then becoming a bit more complete as a physicist. But really, this sort of like, which rabbit hole you go down, that's decided basically by the beginning of your PhD and who your supervisor is.
Yeah, because I was thinking about it. If it is always the supervisor, it sort of seems to be a circle of the same idea with the people going around. So I assume that at some point, people step out and look at the bigger picture, and then maybe try different ideas.
Yeah, it's not always the same ideas, because the supervisor themselves, have been through this process and have taken 4 or 5 steps back, so they have a very large horizon. And doing a PhD now with one person and doing a PhD with the same person 5 years ago or 5 years in the future, you may end up working on very, very different things. So it's not like these people are always doing the same thing. They're evolving, and depending on the field, but very fast sometimes as well. But they will be the ones to sort of, because they'll make you work on whatever they're working on at that time. So I don't think it's circular at all. I think it's just, the field is evolving as a whole, and there's several different fields that are evolving, and, like this big plane, right? And you're kind of like a fly, and then, you apply for PhDs and you accept one, boom, okay, you landed somewhere on this plane. And then basically what ends up happening is, you evolve on this plane and you spread out on this plane, basically. And sometimes you can even change fields a bit, or subfields for sure. So that's kind of how it works. And I don't think it's circular. I mean, I think it's constantly evolving. Of course, there's something very interesting in physics, is that, often things have been studied in the past, maybe superficially, or maybe they didn't have the mathematical tools to study them. And so we revisit ideas from the past a lot. In this analogy or in this picture that I had before of toy models, sometimes, okay, we have a first toy model, and that toy model is too hard. So we come up with a simpler one. Say that toy model was formulated, I don't know, in the 80s, but it was too hard. So, okay, we go to a simpler one, then we spend 2 decades on the simpler one. And then we develop new tools, and we realize, now maybe we're actually capable of doing the other one from the 80s. So we go back to ideas from the past that were too hard at the time, but now we have new tools to study them. So it's not really that it's circular, but there's loops feeding in from the past as this plane evolves.
Our next question is about what's termed publish or perish. Right. First of all, does it exist? Second, if it does, how early does it begin to impact scientists? And in general, what are its effects? Like, how does it take form?
Yeah, so it's absolutely a true thing.
Hmm.
It's just the way science is / has become. I think it's become a lot worse. I think it's a problem. I don't pretend to have the solution out of this, but it is a problem. It's just, this is maybe something that I wish I was told more, is I think science has become more and more and more competitive. And when you ask people that have been through the process, typically they're older, so they've been through the process at a time where it was very competitive, but less than it is today, as it keeps getting more competitive. So because it keeps getting more and more competitive, the overall pressure is just bigger, and maybe the biggest avatar of this pressure is the publication pressure. And so you just have to publish a lot, and that's how it is. And that's a bit annoying because, sometimes the deep questions in science are not easy. I mean, almost always the deep questions are not easy, right? So by forcing people to publish a lot, sometimes there's the trend that you induce slightly more superficial work than if you would let people run for 3 years. Now, the hope is that, yes, there's this pressure when you're young and before you get a job, and then eventually you get a tenured job and the pressure completely drops, which is not actually true because you have to still apply for grants. And again, publication matter for grants. So it never really stops, but at least then you can think about deeper questions once you have a permanent job. But I think that's sort of like the hope, but we've reached a level where it's really, everybody is in this publish or perish mood. And I think to some extent it's hurting a bit research as well, because it's making it be a bit more superficial than what it needs to be. Yeah, go ahead.
What do you mean by superficial? Like, how does that look?
Well, it's just that, say, the types of questions you're going to study are the ones that can produce a paper with good confidence in 6 months, right?
Okay. Yeah.
If there's this other topic that, maybe the answer you'll get will be much more interesting, but say you will only publish after 3 years. 3 years is infinity for a postdoc like me, because you reapply for a job every 3 years. So if your entire activity during 3 years has been to publish, one paper, well, maybe it's, a groundbreaking paper and you publish the day before applications, and then maybe you're safe. But most likely, the system doesn't let you do something like that. So the system pushes people in directions that can produce papers every 6 months. And sometimes those are still interesting, but some other times it just makes people do stuff that's less interesting, but that, it's just a calculation that I can do. It sometimes that's a little bit the risk, is that it pushes people to do things just that they can do. But that's not what science. You should be doing what you should do, what's interesting to do. So that's sort of the trade-off. And of course there's a balance, and it's also important to have realistic goals where you will produce something. But I think this publish or perish mentality is pushing it a bit on the side of, let's just do something that will yield a result, without thinking sometimes hard enough on whether the result is really interesting and people will really care about it or not.
I suppose related to this, like, what do you think are some unpleasant aspects of being a scientist? Like, this can be specific to like your field in physics, or like more generalized as with being a scientist on whole.
Yeah, so good. Let's talk about the downsides, because there are some. So there's this pressure. I mean, overall, you need to be pretty solid to endure this pressure. There's the pressure of publications. There's this competitiveness that's around you. Sometimes it's not in your day-to-day life. Like, you may have amazing atmosphere with your colleagues and your life is good, but still the system is constantly pressuring you and making you compete against one another. And there's some fields where it's even bad. Like, I've heard of stories. Doesn't happen in my field really, but there's 4 new PhD students in a lab one year, and they're not allowed to talk to each other. They're given a project. They have to go ahead and do it. What they don't know is they've all been given the same projects. And it's the first one that succeeds that gets the paper, and the other 3 have spent a year working on nothing. And this is not just like this type of mentality. This exists, and that's very unpleasant, right? I mean, we're being recorded, so otherwise I would use a less polite word, but it's not okay, and this exists. I'm not saying that it's like this everywhere. That's absolutely not true. I think there's also a lot of sane environments, but these types of things do exist, and it's not okay. And it's the type of thing sometimes you end up being in a situation you can't tell necessarily in advance that it's going to be like this. So you end up sometimes in situations like this, and it can be tough. The other thing is that it's also, it's not always a friendly environment. So, I wish that I could say that, science is a world where you come and everybody's nice to you and you can ask all the questions and they're like, oh, that's so interesting, let me explain it to you. But that's not how it works. And sometimes it's a lot more intimidating than that. You have to, especially as a young scientist, part of me maturing as a physicist was understanding that I can just ask questions, and every now and then I'll ask a stupid one, sure, and it doesn't matter. But as a grad student, you're not like that at all. You're like, oh my God, what if I ask a stupid question? And that's not a very healthy environment. We should be in a world where you just ask, and nobody's going to make you feel like you're stupid if by chance your question was stupid. And so it can be a bit intimidating like that as well. And part of growing as a scientist is growing out of that, but it's certainly there at the beginning. That's another negative side. And then the last one is related to mobility/job security. You have to move a lot. Some people enjoy that. Typically, many people enjoy it at the beginning. They're like, oh, it's great. I get to go across the world for 3 years and then back across the world for another 3 years. And that's fun for like 1 or 2 cycles. And then you grow older, you have partners or family or kids or whatever, and life pressures start getting higher, and then you have to move again and again, and then it becomes being very heavy. And also there's the fact that there's absolutely no security that you'll get a job at all. So you might dedicate 15 years of your life for this and then not end up with a job.
And so do you think that these are the reasons why people may leave academia and leave academia? I suppose on that, like, what are the other places that they can go if they do leave? But so it's just a 2-part question. Yeah. So are there any other reasons why people leave, and also where can they leave to? What generally happens?
Yeah, there's many reasons why people leave. People leave because some of them were not really into academia in the first place. They say just wanted to do a PhD. I think the numbers roughly are like after PhD, I think at least 50% of the people don't go further. This is like a worldwide, field-wide stat or something like that, right? So many people, they just wanted to do a PhD. And this is something that I should say is, this is my personal opinion, but I think there's no harm in doing a PhD. It's only, at that stage, it's only positive. You'll learn how to treat problems. It'll be interesting for you on the job market afterwards with a PhD. It'll open new jobs that you wouldn't have access to without it. You'll learn new things. You'll be frustrated sometimes, many times, but it'll be very fun some other times. So the PhD is a win-win, I think. And a lot of people understand that, and that's why a lot of people do PhDs and leave right after. It was clear from the beginning, they'll say, I want to go in finance and be a quant. And in many places, you have to have a PhD to do that. So people just do a PhD in physics, say, or in math. So that's one of the reasons. And then other people leave because they just stop having fun. That happens too. You may very well enjoy doing your PhD, but then you realize this life is just not fun anymore, and so they quit. So that's another reason. And then sometimes people can't take the pressure anymore, so they just quit. So there's many reasons. And sorry, there was another part of the question, which is, what was the first part of the question?
So where people can
what
move
else
to.
you do?
Yeah.
So typically industry in some form or another. There's quite a few people that move to teaching as well. I think those are the two sort of for my field in physics, it was for a long time, it was like either finance or teaching. Those were like the vast majority of what people would leave physics to do. Now it's a bit different because it's diversifying a bit, and also so companies are much more attractive than before. Before it was just finance, but now, you know, a lot of companies have research aspects to them. Google has like a huge research center. And I know many people from my field that have left to go to Google, where they do research in one way or in one form or another. Maybe, you know, research on machine learning and AI, or some other. And some of them, you know, leave to first do research there, but end up actually just liking coding and just do coding. People have left for Facebook, for Amazon. I know like a lot of, and I think these companies have very good conditions and are making things more and more attractive. And so, you know, in some sense, academia is becoming worse and worse, or there's more and more pressure. It's harder and harder. And on the other hand, companies are becoming more and more attractive. And so that's draining people away as well. Mm-hmm. This is something that I've really seen in my field, and it was not like this 5 years ago. It was not like this when I was a PhD student. Mm-hmm. This has really developed over. People were still leaving, but this sort of like what I've seen is very successful people that could easily get a job, just leave because, you know, it's just so much, conditions are so much better in industry.
Mm-hmm. Sure.
Right. Another sort of unpleasant aspect of being a scientist that we've heard from a few other scientists as well is the whole idea of imposter syndrome, in which like scientists sort of pretend to, in one aspect, pretend to belong to the environment that they're in, and two, that they always feel like they don't belong to the environment. You know, and that's where the imposter syndrome comes from. Did you personally experience it, and if so, how did you overcome it? Or if not, what are your opinions about it?
No, I don't think I personally experienced imposter syndrome. I definitely saw friends around me, not like, you know, some of my colleagues I'm very close to, their friends go through this, and this is a real thing. And this goes back a little bit to this atmosphere I was saying, this non-friendly atmosphere as well. It certainly doesn't help, right? You know, if you're already questioning whether or not you belong, and then, you know, one day you're brave enough and you go and you ask your question in the seminar, and they bite your head off, that surely doesn't help, right? So I think, yeah, this is one facet of this environment that can be hostile sometimes. And it's a real thing. I know people that have gone through it. And yeah, like as you say, it also comes from the fact that everybody's sometimes trying so hard to make it look like they're natural and they're confident, and they're that it makes it just harder, both sometimes for those people themselves and for others around them, because they realize that no, actually, not everybody is super confident. And yeah, so yeah, that's I don't think it's something that I've personally experienced. You know, maybe I was lucky enough to have scientist parents, so I don't feel, so maybe I feel like I belong more because of that. I don't know. This is now we're getting into, I guess, pretty personal stuff. I can't. I guess I'm not a shrink, but maybe a shrink could tell me. But yeah, I never really had this feeling, but I've definitely seen people around it. And even though I didn't have imposter syndrome, I think I was very. So I don't consider myself a shy person at all, but I was terrified to ask questions in talks for a very long time. And at some point I had just to learn to get over it. So that's something that I was affected by. And yeah, that comes from this atmosphere. So I think in one form or another, we all kind of go through this. And it's tough. And it sucks. It shouldn't be this way. I don't really know why it is. Like somehow, the only thing I can see is that, you know, everybody that has been through it had to go through it. So they perpetuate it for the next generation because, you know, that's how it is. I went through the trenches. You will go through the trenches. It's the only explanation I can find, and it makes no sense, and we have to do something about it, but I don't think it's really changing. Yeah.
Yeah, so sort of approaching the end of our questions, we have these two questions as a constant in the end. Um, as we said, there may be other people, probably thousands of people around the world who would like to pursue their careers in science as well, but again, they don't have the access to to the people who've experienced it and to maybe the knowledge base for it. What is your advice for young people pursuing anything in life?
Um, I would say have fun. I think it's supposed to be fun. The day it stops being fun, leave. Don't. I mean, of course, this. You know, you can be frustrated for a week because nothing's working. That's not what I mean. It's sort of at the bigger level, right? Like you have to be having fun, or at least there needs to be enough moments of fun that separate the frustrating moments. That overall, it's fun and enjoyable to do science. You will do better science if you're having fun. If you're not having fun, you will not do good science. Period. So have fun. I think that's number one. Work hard because yes, you will have to work hard. Don't overwork yourself either, but just work hard. Try to find the balance, um, and continue for as long as it's fun. And I think probably a fair advice to give people now, because science is so competitive and it's so hard to get a job. Um, Try to be very careful with starting off saying, I will be a university professor. I think it's great to have that as a goal, but it's hard. It's really hard, competitive. Maybe even if you do everything right, maybe you're a bit unlucky because the field you did your research on becomes less trendy by the time you're done or whatever. Things can happen. Okay, so even if you did everything right and you're very, very smart and very good, sometimes it doesn't work out that way. Um, so it's fine to have that as a goal, um, but but be very careful with thinking that that's how it's going to work out. And so because of that, go through the process and continue as long as it's fun. As long as you're happy in your life and you're having fun doing your work, then I think it's good to go. And hopefully that takes you all the way, to the end and to a faculty position. Maybe it'll take you halfway through and then you'll branch out because you'll realize you're having more fun in industry in some other way. Um, there's various trajectories. But if you're really unhappy, don't continue. Don't like bang your head against the wall. It's supposed to be fun. I think that's my number one advice.
So that's actually a good segue to the next thing, because what we also want to do is we want to compile a book of quotes, right, of just some general words of wisdom, like a sentence or two. So what what do you think you can add to that? Have
Oh
fun
God.
works. I think it's a good candidate.
Yeah.
If you want anything else to go in there.
Definitely.
Yeah, I don't think I can. I'm not that good with words. That's another reason why I went to math and physics. Um, yeah, I think I'll leave it at that.
Yeah.
Science is about fun.